Lake Superior swallowed 3 ships in a single night. Not in some ancient maritime disaster from the 1800s. November 10th, 1975. Modern ships with radar, radio, and weather forecasts. Gone in minutes. The waves that took them down weren't supposed to exist in a lake. Ocean waves? Sure. But freshwater. Scientists are still trying to figure out how water that's technically landlocked can generate conditions that rival the North Atlantic. Stick around, because what's happening in the Great Lakes breaks every rule we thought we understood about inland water. Let's get something straight right from the start. The Great Lakes aren't lakes. Not really. They're inland seas that happen to be filled with fresh water instead of salt. Lake Superior alone contains enough water to flood all of North and South America under a foot of water. Put all 5 Great Lakes together, and you've got 21% of the world's surface freshwater. 6 quadrillion gallons. That's not a typo. 6 with 15 zeros after it. But size isn't what makes them dangerous. What makes them dangerous is that they act like oceans while being trapped in a relatively small space. They generate waves that shouldn't exist. They create weather patterns that defy prediction. They produce phenomena that scientists observe, document, and then admit they don't fully understand. And the footage coming out of the Great Lakes over the last few decades is getting harder to explain. Start with the waves. You've probably seen ocean waves. Maybe you've been to a beach, watched the surf roll in. Ocean waves can get massive, 60 or 70 feet in extreme storms. But ocean waves have thousands of miles to develop. They build up gradually as wind pushes across vast distances of open water. The Great Lakes don't have that luxury. Lake Superior is about 350 miles long. Lake Michigan is 300 miles. These are large distances, sure, but nothing compared to the Pacific Ocean. So you'd expect smaller waves, right? Wrong. The Great Lakes regularly generate waves over 20 feet high. In extreme conditions, waves over 30 feet have been documented. In 2017, a buoy on Lake Superior recorded a wave 28.8 feet high during a storm. That's taller than a 2-story house, on a lake. And here's where it gets weird. Those waves are steeper and closer together than ocean waves of similar height. Ocean waves are usually spaced far apart. The wavelength, the distance from one wave crest to the next, can be hundreds of feet. Great Lakes waves are compressed. The wavelength is shorter, sometimes only 50 or 60 feet between crests. What this means in practical terms is that ships get hit by waves more frequently. Instead of riding up one wave and having time to recover before the next one, they're getting pounded continuously. Moanim. No break, no recovery time. Why does this happen? Scientists think it has to do with fetch, which is the distance wind can blow across open water without obstruction. The Great Lakes have enough fetch to generate significant waves, but not enough to spread those waves out. They're compressed, concentrated. It's like the difference between a lazy river and rapids. Same amount of water, different energy distribution. But there's another factor that scientists are still trying to understand. The lakes are shallow compared to oceans. Lake Superior averages about 500 feet deep. Sounds deep until you realize the Atlantic Ocean averages over 12,000 feet. When waves move into shallow water, they change behavior. They get taller, they get steeper. The energy that was spread out over a larger wave in deep water gets concentrated into a taller, sharper wave in shallow water. The Great Lakes exist in this weird middle ground. They're deep enough to generate waves like an ocean, but shallow enough that those waves behave unpredictably. Add in the fact that the lake bottom isn't uniform. There are underwater ridges, trenches, and sudden depth changes, and you've got waves that can amplify, combine, or transform in ways that are hard to predict. Then there are the rogue waves. Yeah, rogue waves. These are the waves that shouldn't exist according to classical wave theory. They're waves that are more than twice the height of the surrounding waves, appearing seemingly out of nowhere. For years, scientists thought rogue waves were maritime folklore. Stories sailors told to explain why ships sank in conditions that didn't seem that bad. Then in 1995, the Dropner wave hit an oil platform in the North Sea, an 85-foot wave in seas where the significant wave height was only 40 feet. Suddenly, rogue waves were real, documented, measurable. They can happen in the Great Lakes. In fact, they do happen in the Great Lakes. There's video footage of rogue waves on Lake Superior and Lake Michigan. Massive walls of water appearing suddenly, hitting shore or striking ships, then disappearing back into the regular wave pattern. Scientists studying this phenomenon think it has to do with wave interference. When multiple wave patterns intersect at just the right angle and timing, their energy combines. Instead of two 10-foot waves, you get one 25-foot wave. Just for a moment. Then it collapses, and the energy disperses. But predicting when and where this will happen? Nearly impossible. The variables are too complex. Wind direction and speed, existing wave patterns, currents, water temperature, atmospheric pressure. All of these factors interact in ways that even the most advanced computer models struggle to predict accurately. So ships on the Great Lakes are dealing with waves that can literally double in height without warning. Now let's talk about the weather, because the Great Lakes create their own weather. This isn't speculation. Meteorologists have documented something called lake effect weather, and it's fascinating and terrifying in equal measure. Here's how it works. Cold air blows across relatively warm lake water. The water evaporates rapidly, loading the air with moisture. That moisture-laden air then blows over land, where it cools rapidly and dumps all that moisture as snow or rain. Lake effect snow is legendary around the Great Lakes. Buffalo, New York, can get buried under 6 feet of snow in a single storm. But here's what most people don't realize. Those same conditions that create lake effect snow also create incredibly violent conditions on the lakes themselves. The rapid evaporation and temperature differences create intense localized storms. Wind speeds can increase dramatically over very short distances. Visibility drops to near zero in minutes. Ship captains call these whiteouts, and they're deadly. 1 minute you've got reasonable visibility and manageable conditions. The next minute you can't see 50 feet in any direction. The wind is increased by 30 miles per hour, and waves are coming from a completely different direction than they were 5 minutes ago. Modern radar helps, but radar can't tell you about sudden wind shifts or rogue waves. There's also something called a seiche, pronounced sesh, and if you've never heard of it, you're not alone. Most people haven't, but people living around the Great Lakes know about seiches, and they're learning to take them seriously. A seiche is essentially a standing wave in an enclosed body of water. Think of it like sloshing water in a bathtub, but on a massive scale. Here's what happens. Strong winds or rapid changes in atmospheric pressure push water from one end of a lake to the other. The water piles up on one shore, sometimes raising the water level by several feet. Then the wind stops or the pressure equalizes, and all that water sloshes back. It can oscillate back and forth for hours or even days, gradually losing energy. During a seiche, the water level can change by 10 or 15 feet in a matter of minutes. Boats tied up at docks suddenly find themselves high and dry, or underwater. Marinas get flooded. People standing on shore can suddenly find themselves chest-deep in water that appeared out of nowhere. And this happens without warning. 1 minute the water is calm. The next minute it's rising or falling rapidly. Scientists can measure seiches happening. They've got gauges that track water levels constantly, but predicting exactly when one will occur and how extreme it will be, that's harder. They need to know wind speed and direction, atmospheric pressure changes, even the shape of the lake bottom, because that affects how water moves. Get any of those variables wrong, and the prediction is worthless. There's footage from 2018 of a seiche on Lake Erie that's genuinely unsettling. The water along the shoreline drops about 6 feet in 15 minutes. Boats that were floating are suddenly sitting on muddy lake bottom. People are walking around on exposed areas that were underwater moments before. Then the water comes rushing back faster than people can run. Several people had to be rescued because they walked out onto the exposed lake bottom to look around and couldn't make it back before the water returned. The Great Lakes also experience something called meteo tsunami, which is exactly what it sounds like. A tsunami caused by weather, not earthquakes. When a strong squall line or intense weather system moves across a lake at just the right speed, it can create a wave that builds up energy as it moves. When this wave hits shore, it can surge inland like a tsunami. We're not talking about 100-foot walls of water, but 10 or 15-foot waves hitting shore areas where people expect maybe a foot or two. In 1954, a meteo tsunami on Lake Michigan killed 7 people in Chicago. The wave was about 10 feet high when it struck. People fishing from piers were swept into the lake. No warning, no time to react. One minute they're fishing in calm conditions. The next minute a wall of water washes over them. Scientists didn't even understand what had happened until decades later when they went back and analyzed the meteorological data. Meteotsunamis are rare, but they happen often enough that scientists are trying to develop warning systems. The problem is the same as with rogue waves and psyches. Too many variables, too much complexity. By the time you detect the conditions that might create a meteotsunami, it's often too late to warn people. Let's get back to ships for a minute, because the Great Lakes have a reputation for swallowing ships whole. The most famous is the Edmund Fitzgerald, which sank in Lake Superior on November 10, 1975. This was a massive ship, 729 feet long, carrying 26,000 tons of iron ore. Built in 1958, considered one of the most modern and capable ships on the lakes. It left port in good weather, encountered a storm, and simply disappeared. All 29 crew members died. The ship broke in half and sank in about 530 feet of water. What caused it? Nobody knows for certain. The official investigation concluded that the ship took on water through damaged hatches and eventually lost buoyancy. But that doesn't explain why the ship broke in half. Some researchers think a rogue wave hit the ship. A wave so large and powerful that it literally bent the ship until it snapped. Others think the ship bottomed out in a trough between waves, hitting an underwater ridge or shoal. Still others think the ship was caught in a psyche or hit by multiple waves in rapid succession. The wreck has been photographed and studied extensively. The bow and stern sections are about 200 feet apart on the lake bottom, but examining a wreck in 530 feet of cold, dark water is difficult. And even with modern technology, scientists can't definitively say what sank the Edmund Fitzgerald. They've got theories but no certainty. And if they can't explain what happened to a modern ship with a known route and detailed weather data, what does that say about their understanding of the lakes? The Edmund Fitzgerald isn't unique. Estimates vary, but somewhere between 6,000 and 10,000 ships have sunk in the Great Lakes. Some of those are old wooden ships from the 1800s. But plenty are modern steel vessels that should have been able to handle the conditions. The lakes have a nickname among sailors. They call them the graveyard of the Great Lakes. Lake Superior gets that title most often, but all 5 lakes are dangerous. What makes these shipwrecks particularly mysterious is that many of them happened quickly. Ships would be sailing along, in communication with shore or other vessels, and then just vanish. No distress call, no time to abandon ship. Nothing. One moment they're there, the next they're gone. Reconstructing what happened is nearly impossible. You've got the wreck on the bottom, if you can find it, and you've got weather data. But connecting the two, that requires assumptions and educated guesses. Modern ships have better technology: GPS, satellite communication, advanced weather forecasting, radar that can see through storms. But the lakes are still dangerous. In 2001, the freighter Maumee sank in Lake Erie during a storm. Luckily, the crew was rescued. In 2017, the tug John D. McKean sank in Lake Michigan. Again, crew rescued, but the ship went down. These aren't ancient history. These are modern vessels with modern safety equipment, and the lakes are still taking them. The ice is another factor that scientists struggle to predict and understand. The Great Lakes freeze partially or completely during winter. Ice coverage varies year to year depending on how cold it gets. But some years the lakes are 90% covered in ice. You'd think ice would make the lakes safer, right? Everything is frozen solid. No waves, no storms. Wrong again. Ice on the Great Lakes behaves unpredictably. It forms, breaks up, refreezes, shifts around. Wind can push ice flows into pressure ridges, massive walls of broken ice, pushed up by the force of ice sheets colliding. These pressure ridges can be 30 or 40 feet high. They form suddenly and they can shift and move. A clear channel through the ice can close in hours as ice flows drift and collide. Ships trying to navigate through ice deal with constant danger. The ice can damage hulls, jam rudders, or trap ships completely. Several ships over the years have been frozen in place and had to wait weeks or months for icebreakers to reach them. And even in modern times, with satellite imagery and ice monitoring, ships still get trapped. The ice just doesn't behave predictably. Then there's something called ice volcanoes that have been documented in recent years. These form on the shore, when waves break through thin ice, creating a cone-shaped mound of ice with a hole in the center. Water and ice spray out of the hole like a volcano. They can grow to 20 or 30 feet tall. Scientists think they understand the basic mechanism, but predicting where and when they'll form is difficult, and they're potentially dangerous because the ice around them is unstable. The Great Lakes also experience dramatic water level fluctuations that scientists struggle to predict accurately. Water levels are affected by precipitation, evaporation, runoff from surrounding land, and even how much water is diverted for human use. But the year-to-year variation can be dramatic. From 2012 to 2020, Lake Michigan rose about 6 feet. 6 feet doesn't sound like much, but when you've got thousands of miles of shoreline, a 6-foot rise floods huge areas. Docks that were fine are now underwater. Beaches disappear. Homes built near the shore are suddenly waterfront in a bad way. What caused the rapid rise? More precipitation, less evaporation, probably some changes in how water flows through the lakes. But climate models didn't predict this rise. It caught scientists and residents by surprise. Now water levels are dropping again. And again, the models aren't matching reality perfectly. The Great Lakes system is too complex, too many variables. Scientists can make educated guesses, but they're learning that the lakes don't follow predictable patterns. There's also the current situation with warming water temperatures. The Great Lakes are warming faster than ocean water, about twice as fast according to some studies, which means more lake effect weather, which means more intense storms. It also means longer periods where the lakes don't freeze, which changes wave patterns and coastal erosion. But here's where scientists admit uncertainty. They don't fully understand how warming temperatures will affect the lakes long term. Will storms get more intense? Probably. Will water levels rise or fall? Depends on whether increased precipitation outweighs increased evaporation. Will the lakes still freeze in winter? Maybe, maybe not. The models predict a range of outcomes, which is another way of saying they don't know. Recent footage from research vessels and buoys is adding to the mystery. High-resolution sensors are capturing wave patterns that don't match theoretical models. Underwater currents that flow in unexpected directions. Scientists are collecting more data than ever before, and that data is revealing how much they don't understand. One research project has been deploying autonomous underwater vehicles to map the lake bottoms in detail. They're finding features nobody knew existed. Underwater channels, sudden drop-offs, areas where currents concentrate. This is useful information, but it also highlights how little was known before. We've mapped the surface of Mars in more detail than we've mapped the bottom of Lake Superior. What does all this mean for the future? The Great Lakes aren't getting calmer. If anything, climate change is making them more volatile. More intense storms, unpredictable weather patterns. Scientists are working hard to improve prediction models, but they're honest about the limitations. The lakes are complex systems with countless variables interacting in nonlinear ways. Small changes can have big effects. Chaos theory applies. The footage coming out of the Great Lakes, the documented rogue waves, the psyches, the meteotsunamis, the ship disappearances, all of it points to one conclusion. These aren't calm, predictable bodies of water. They're volatile, dangerous, and not fully understood. Scientists can explain the basic mechanisms, but predicting specific events, that's still beyond current capability. People living around the Great Lakes are learning to respect the water. Not just fear it, but respect it. Understand that it can change from calm to deadly in minutes. Monitor weather constantly. Have escape routes planned. Don't assume that because you're on a lake, you're safe. The Great Lakes are a reminder that nature doesn't care about human understanding. The water will do what it does regardless of whether scientists can explain it. And until we develop better models, better sensors, and better understanding, the lakes will keep surprising us. Keep generating waves that shouldn't exist. Keep swallowing ships. Keep defying prediction. Subscribe. More content coming soon.